This is IB HLAA vectors day number 2. We're going to focus today on some vector algebra and unit vectors. Let's get started. All right, so a little bit more today on vector terminology. The first item for this lesson is what's called the unit vector. The unit vector is exactly what you'd think, which is a vector of magnitude 1 unit. The three foundational unit vectors are I, J, and K on the X, Y, and Z axis, respectively. So let's sketch the X, Y, and Z planes, or axes, I should say. Okay, let's say this is X, this is Y, and this is Z. The vector I is a vector of 1 unit in the direction of X. The vector J, 1 unit in the direction of Y, and the vector K, 1 unit in the direction of Z. Now, the terminal point of each of those vectors can be represented by a 3-dimensional column vector, if you will. This right here you can see is a 2-dimensional vector, so that would just be on the real plane, right? But we're going to speak on 3 dimensions here. So if we go 1 unit in the direction of X, 0 in the direction of Y, and 0 in the direction of Z, we would get that unit vector, which we would call I. So really that's I plus 0J plus 0K. Okay, and very similarly, you'd see that, of course, this terminal point here would be the point 0, 1, 0. And likewise, for K, we would have 0, 0, 1. Okay, so with that being said, each of these vectors are unit 1 in measure, in magnitude, if you will. So actually, it's also true that if I wrote out negative I, or negative J, or negative K, the same would be true. Now there are instances, let's say in the real plane, right, where we have, this is R crossed with R, right? So I've got 2 dimensions here. Here I would have potentially 3 dimensions, depending on what I'm considering. But on R cross R, I could have, for example, a vector that looks like this, of length 1 unit, right? So this vector would actually be 1 over root 2 and 1 over root 2, which we could write as I over root 2 plus J over root 2. Now that might kind of ring a bell. That's unit circle work right there. Of course, the magnitude of this particular vector, right, would be 1 unit. So the unit circle actually is going to show up quite a bit as we get going with this. All right, so let's take a look at an example here. Let A be the vector 3i plus 2j, and B be this vector with a bunch of fractions. Okay, I typically like to work with what I call column vector form. So I would really write A as 3, 2. So my first number is the change in the x direction, second number change in the y direction. And B I would refer to, typically, just less writing, as negative 3 halves, 7 halves, 1. Okay, preference, it's all up to you, unless you're prompted to use one or the other in your answer. Part A says to find 2 vectors in the direction of A, one of which is a unit vector. Okay, so I'll find, how about a vector in the direction of A that has, I don't know, I don't care about the magnitude, I just want it to be a different length than A, so just in the direction of A. So what we know is that we can take any vector and just multiply it by a constant, and that would be parallel, okay, to vector A. Now, if lambda is less than 0, it's headed in the wrong direction. So we want this to have the same coefficients, right, as A, or excuse me, the same sign in the coefficients. So if A equals 3, 2, okay, a vector in the direction of A, let's call it W of A, could be, I don't know, let's say 5 times 3, 2. Okay, we don't know yet the magnitude of A, but we do know that W sub A would be 5 times the magnitude of A. So we'd have 15 and a 10. Okay, so now let's talk about a unit vector in the direction of A. Well, in order to know the coefficients or the components of a unit vector in the direction of A, we got to know the magnitude of A. So how we find the magnitude of A is we use the Pythagorean theorem. Right, so for example, if I was here at 0, 0, you can always just kind of plot this as a starting point of 0, 0, and I want 3 in the direction of x and 2 in the direction of y. This is an example of one of the vectors representing A. Okay, so using Pythagorean theorem, I would have 3 squared plus 2 squared, which would give me the magnitude of A, which is root 14. Now if I want a unit vector, which I denote as U, in the direction of A, I take A, right, which is 3, 2, and I multiply it by the reciprocal of its magnitude. Okay, if I do that, what I'm doing is I'm taking and I'm shortening A down to a length of 1. Okay, so now I've got U sub A. U sub A. That's a unit vector in the direction of A. Now that can be written also in this form. Not necessary, but could be written as 3 over root 14, 2 over root 14. That would be a unit vector in the direction of A. Part B says find a vector of magnitude 20 in the direction of B. Magnitude 20 in the direction of B. Okay, so I got to find the magnitude of B first. Let's find the magnitude of B. Now in 3 dimensions, nothing changes. We just use the 3 components for the magnitude of this particular vector. So we'll take the x component, square it, that was a negative. Y component, square it, and z component, square it. Okay, so what we end up getting is the square root of 9/4 plus 49/4 plus 1 squared, which is 1. I'm going to write it as 4/4. Okay, so the magnitude of vector B will equal, oh gosh, what is that? 62. Square root is 62 over the square root of 4, which I'm going to write as 2. Okay, so that's the magnitude of B. Now I'm going to take B and I'm going to write a vector of length 20 in that direction. So I'm going to use a T for 20. 20 in the direction of B would equal the unit vector, right? So let's say I take, I don't know exactly what this would look like, but let's say I have the three-dimensional axes. I'd like you to try to visualize this. We'll see how well I can do it. So here's x, here's y, here's z. Okay, so I'm going to go left 3 halves. So that's negative 3 halves I. I'm going to go forward 7 halves. So that's 7 halves j. And then I'm going to go up 1. It's going to be 1 k. So if you can imagine, it's this vector right there. Okay, so I can use the Pythagorean theorem, right, like I did here, to find the magnitude of B. So really, vector B is this vector in yellow, right? So if I take this and I shrink it down, I don't have a different color, so I'm going to go like this. And I shrink it down to a unit length, but then I multiply it by 20, right? So then I multiply a unit vector by 20. Right, this would be TB. Okay, so let's see what that would be. So I'm going to take the unit vector, which would be root 62 over 2, times b, which was negative 3 halves, 7 halves, and 1. And I'm going to multiply it by 20, right? I'm going to just multiply that by 20. Now I'm going to clean that up slightly. So the 20 and the 2 will reduce to a 10, and I'm going to distribute a 10. I'm going to leave well, actually, we'll clean this up entirely. Let's do this. You can see for the x component that what I would end up with would be, it looks like to me, negative 15 root 62. You can work that out on your own. Okay, here I would get 35 root 62 for the y component, and then for the z component I would get 10 root 62. Okay, let me check my numbers. 5, negative 15, yep. 535, yep, that looks good to me. So that would be a vector in the direction of b that has a magnitude of 20. All right, let's continue. Okay, multiplication of a vector by a scalar. We talked about this in lesson 1. Actually, we're just going to take this to a different level to some extent, so follow me as I go here. Okay, so in this example, what we have is we have vectors a and b clearly on r cross r. Okay, so all that means is 2 dimensions. Okay, in a, I'm going to write a as negative 1, 1, keep it simple. I'm going to write b as 2, negative 3. Okay, so in part A, I want to find 2a minus b. Well, that's relatively simple. I'm going to take 2 times a, which is negative 1, 1, and I'm going to subtract b, which is 2, negative 3, and I'm just going to combine their components. So this will be negative 2, 2, minus 2, negative 3, which reduces down to, that looks like a negative 4 and a positive 5. So I could write it that way, or I could write it as negative 4i plus 5j. All right, let's look at part B. Part B is interesting. It says express a new vector c as a linear combination of a and b. Okay, so let's kind of expand upon this idea here. Okay, so this vector c, which is 4 and a negative 7, I'm going to write as a linear combination of a and b. So what I'm going to do is I'm going to write constants, right, some kind of multiplier times a plus some kind of multiplier times b. So this will be vector a, this will be vector b. Well, vector a is negative 1, 1. Vector b is 2, negative 3. Okay, now what I'm going to do is I'm going to create 2 linear equations, and I'll do that momentarily here. So I'm going to take the x component, which is right here, right, which shows up in all 3 of these vectors. So what I could say is that 4 is equal to negative lambda plus 2 mu. Okay, and with the y components, I could say that negative 7 is equal to lambda minus 3 mu. All right, so what I'm going to do now is I'm going to solve for lambda. So in this case, lambda will be equal to 2 mu minus 4. And over here, lambda is going to be equal to 3 mu minus 7. All right, now what I'm able to do is I'm going to be able to eliminate lambda entirely. So it's going to allow me to find mu. Okay, which looks like if I solve here correctly, I get 3 equals mu. Which again, I can go back solving this linear equation. It doesn't matter what I pick. Maybe I'll go right here. Therefore, lambda will equal 3 times mu, which is 3 minus 4. Okay, so in essence, what I end up with is I end up with the lambda and mu such that this would be true. Therefore, I'd get 5 for lambda and 3 for mu. Whoops, goofed up my algebra. Maybe you caught it. I didn't. This should be a 2, which would make that 6 minus 4, which would make lambda 2. Okay, so what does that tell us? That tells us that C is actually equal to, based on our definition, lambda times A, which is 2A, plus mu times B, which would be 3B. So there you go. That is C as a linear combination of A and B. Okay, position vector time. A position vector, or a vector P, that starts at the origin and ends at a point P on the same plane is called a position vector. Okay, we write that P equals OP, which is equal to x plus xi plus yj, which we could write in column form as xy, where x and y are called the horizontal and vertical components of the vector P, respectively. So a direction vector is a vector that notes the direction of travel from one point to another. So, for example, if I'm given, point A and point B, okay, here's point A, which is 2, 5. Here's point B, which is 7, 8. So the direction vector from A to B will be all the points where we end up. So your x of B and your y sub B minus the points where you come from, x of A and y sub A, which in this case would be 7 minus 2 and 8 minus 5. So this direction vector in particular, wow, tired today, is 5, 3. Okay, so if you looked at this vector here, you might notice, if you're just thinking, linear in nature, if I took y minus y over x minus x, I should get the slope. So the slope actually does show up in the vector, but our traditional sense of thinking y in the numerator, x in the denominator, or change in y, change in x, just kind of shows up in a different way. So here's your change in y, here's your change in x. Now if I wanted the vector BA, well, we know that BA is the opposite of AB. So BA would actually be equal to -5, -3. Okay, let's go ahead and look at another example here. Given a parallelogram ABCD with points A, B, and D given, find the coordinates of C. This is a classic example of when you'll use this idea, okay, of a direction vector. So let's place some points out here. Let's go A right here, which is -2, 1. Let's go B right here, which is 3, 0. Let's go C out here, which we don't know the coordinates to, but we'll find them. And we'll go D up here, which is the point 0, 2. Now, what we do know is we have a parallelogram. What that tells us is that the opposite sides are equivalent vectors. Therefore, AD, okay, this vector from A to D is equivalent to the vector from B to C. Okay, well, that's actually really helpful because the vector from A to D, right, which would be the points of D minus the points of A minus a -2, should be equivalent to the points of C minus the points of B. Okay, so I'm going to take x minus, that's wrong, how about x minus 3 and y minus 0. Okay, so let me repeat what I just said. These are the points, both x coordinate, oh, that's actually really wrong. Let's flip this around. We want our x coordinates on top and our y coordinates on the bottom, right? Change in x, change in y. Glad I did that. 0 minus a -2, which is 0 plus 2, and 2 minus a 1. Okay, so now what I know is since these vectors AD and BC are equivalent, then these components should be equal, right? Therefore, what I can do is I can set these equal to each other and solve for x and y, which means I'm now solving for point C's coordinates. So that would mean 2 is equal to x minus 3, which tells me that x equals 5, and 2 minus 1, which is equal to 1, is equal to y. Therefore, y is equal to 1, and therefore the point C is the point 5, 1. Okay, so as you can see, as you're working through this, just make sure you keep the x-coordinate first in the column vector form, y-coordinate second. All right, let's look at another example. All right, example, no number attached to it. That's fine, whatever, we don't even care. Okay, it says let A, B, C, D, E, F, G, H be a parallelepiped. That's fancy for prism. With vertices 0, 0 for A, 2, 3, 0 for B, D is that, and E is that. Find the coordinates of C and G. Now, what it means to be a prism is that each of these vectors, right, A to B, D to H, C to G, and B to F, those are all equivalent vectors. Okay, so it means they have the same direction, same magnitude. So any sides that would be parallel to each other are also equivalent to each other, right? And back to equivalence, that just means that if you connected their endpoints, right, if I connected A to F and B to E, they would have a common midpoint. All right, so now let's find point C. All right, so let's go like this. Let's first take, in order to find C, let's take and look at the point A plus the vector from A to D. Okay, so the point A I know is the origin, 0, 0, 0. If I go in the direction of AD, I will find myself at point D. Okay, so A to D is all the values of D, coordinate minus the values of A. So this is kind of redundant. It might seem like, why do I need this? But it'll kind of come to a head here in a second. All right, so there's point D, right? So if I want to get to point C, what I want to do is I want to take and travel along this vector from A to D, and then follow it up with this direction vector from A to B. Since A to B is equivalent to D to C, in essence what I'm doing is I'm taking AD and I'm adding DC to it. And what that does is that gives me a vector from A to C. Okay, so let's talk about that. Well, I know AD. AD is -1, 4, -2. I know DC. Actually, I don't, right? Because I don't know the coordinates for C, but I do know AB. So since D to C is equivalent to A to B, I can use the direction vector from A to B. So let's find A to B. So A to B, since A to B is equivalent to D to C, highlighted in yellow below, all right, A to B would be 2 minus 0, 3 minus 0, 0 minus 0, which is 2, 3, 0. Therefore, these two direction vectors would be equivalent. Now, if I started point D and I head to point C using that direction vector, I will get A to C. A to C would then be 1 and 7 and -2. Now, if I went from point A in the direction of AC, that would get me point C. That's why I went over this idea right here. The reason why that's important is because sometimes this point won't be the origin. When it's the origin, it's simple. It doesn't seem like, hey, I really even need to do any work. I just take the direction vectors AD and DC, and that gets me to point C. But that's only true if the origination point is the origin. So here we go. Let's take this, and clearly what we'll see is that point C is equal to 1, 7, -2. So point C, I'll use the proper notation here, would be 1, 7, -2. All right, let's go ahead and take a look at finding point G. Let's navigate our way to G, and let's go to G from C. So if I took C and I traveled in the direction of G using any one of these 4 direction vectors, I could find that coordinate. So G is actually equal to point C plus the direction vector from A to E. All right, so I'm going to take this vector right here, I'm going to translate it over here, use that same direction, and go from C to G. So G would equal C, which we found in part A, 1, 7, negative 2, plus the direction vector from A to E. The direction vector from A to E, I would use these 2 points, take all the components of E, subtract the components of A, and I would get 1, negative 2, and 6. Again, pretty simple due to the fact that A is at the origin. Okay, so I'm going to add these 2 component vectors, or vertical column vectors, if you will, together, and I get 2 and a 5 and a 4. So that is point G. All right, that's how you use direction vectors. I should probably write G in the proper notation, although this notation right here is not incorrect. I just prefer this horizontal component form right here. That's how you use direction vectors. That's lesson 2. See you guys in the next video.